All right, let's go on a bit of a cosmic treasure hunt. Our treasure, believe it or not, is microscopic dust. Tiny particles collected way up in Earth's stratosphere. Now, they might be pretty much invisible, but they hold the secrets to the birth of our entire solar system. So we're about to piece together a story that's, get this, 4.5 billion years old.
And really, it all comes down to this one question. How can something that small, something you literally can't see, tell us anything about the birth of, well, everything around us? That's the mystery we're going to unravel today.
So, here's our game plan. First up, we've got to prove this stuff is actually from outer space. Then we'll get a good look at it, build a profile of our cosmic dust. After that, we'll check out its family tree, see if it's related to comets or meteors. And then, the really mind-blowing part, we'll see if it holds matter from before the sun was even born. And we'll wrap it all up by looking at how these tiny specks can help explain how whole planets get made.
Okay, so first things first, and this is the big one, right? This dust was found floating around high up in our atmosphere. How in the world do we know it's not just, from Earth?
I mean, the whole investigation pretty much depends on the answer to this. Is it a sure thing? Are these little guys really aliens?
Oh yeah, it's a big, fat, definitive yes. No doubt about it. But you know how science works, right? A simple yes isn't good enough. You've got to show your work. You need the proof.
And the proof? Well, it's basically stamped all over these particles. For starters, they're peppered with these tiny little tracks. Think of them like microscopic bullet holes left by cosmic rays that zap them out in deep space. You just don't see that on Earth rocks. Second, they're loaded with a special kind of heavy hydrogen called deuterium, way more than you'd ever find naturally on our planet. And third, even the gases trapped inside of them have a chemical fingerprint that just screams not from around here. So case closed on that one. These are 100% from space.
So, we've established their origin. They're legit interplanetary dust particles, or IDPs for short. The next logical question is, what are they actually like? What's the deal with these tiny cosmic travelers?
The classic description you always hear is that they look like a cluster of grapes. A kind of fluffy, porous little clump of even smaller grains. And yeah, a lot of them do look like that. But that's not the whole story. Not by a long shot.
The reality is, these IDPs have all kinds of different personalities. Sure, you've got your fluffy ones, but you've also got these really dense, compact little nuggets. It's a huge mistake to think they're all the same. They're a really diverse family.
So how do you sort them all out?
Well, scientists basically shine infrared light on them to get a chemical fingerprint. And based on that, they fall into three main groups. You've got your olivine type, your pyroxene type, and then this third one with a fancy name, layered lattice silicates. All you really need to remember about that one is that it has minerals that were changed by water. Water in space.
And this is where it gets really fun, like a proper detective story. This sorting system isn't just about putting things in boxes. It's about finding clues. Check this out. There was this one particle. They nicknamed it calricin, which is awesome. And it was in that water-altered group, but its light signature was weird. It had this little spike nobody expected. The data suggested carbonates. So they zoomed in with a microscope, and boom, there they were. A tiny little blip in the data led to a huge discovery.
All right, so we know what they are, and we've got an idea of what they're made of. But what's their home address? Are they cousins with things we're more familiar with, like meteorites or even comets? Let's take a look at the family tree.
So, let's put them head-to-head with meteorites first. The big difference you see right away is structure. Nobody's ever found a chunk of meteorite that looks like one of those fluffy IDPs. They're just different. But, and this is really cool, chemically, they share that same telltale heavy hydrogen signature. So they're related for sure, but they're not just miniature meteorites. Something else is going on.
And that something else leads us to the most popular idea out there, that these IDPs are basically dust that's flaked off of comets. It makes a lot of sense, and a lot of scientists are on board with it. But proving it, that's tricky. It's not like you can just fly out and scoop up a piece of a comet, yet.
And there was a big problem. At first, when astronomers looked at the light coming from the dust around a comet, Comet Kohoutek, its fingerprint didn't match any of our IDP types. Not olivine, not pyroxene, none of them. It was a real head-scratcher.
But the answer, it turns out, was so elegant. What if a comet isn't shedding just one kind of dust? What if it's a mix? So they tried it. They combined the light signals from the pyroxene type and the water-altered type, and bang, a really good match.
It's a massive clue that comets are way more complex than we thought, shedding this whole cocktail of different dust particles.
Okay, so we've got a solid link to comets. That's huge, but this is where the story gets profound. We're moving past what is this stuff and into what does this stuff know? Could these tiny particles actually be time capsules from the birth of our solar system?
First, we need to get a term straight: primitive matter. The word primitive here doesn't mean simple. It means pristine, unchanged. Think of it like a fossil that's been perfectly preserved, with a unique chemical signature that says, "I was made right at the beginning, and nothing has messed with me since."
But then, you can go even one level deeper. Primordial matter. Now this is the holy grail for astronomers. This isn't just matter from the early solar system. This is matter from before the solar system. We're talking about actual, original dust from the giant interstellar cloud that collapsed to form the sun and all the planets. It's the literal starter ingredients for everything we know.
So that brings us to the biggest question of all. Could these tiny dust particles we've collected contain actual, untouched grains of that primordial stardust? Is that what we're holding in our labs?
Well, the evidence is complicated. It's tantalizing. On the one hand, their light signature looks a lot like the dust around brand new stars, and that high, heavy hydrogen content, that's a perfect match for what we'd expect from a cold pre-solar cloud. But there's a catch. Our theories predict that true interstellar grains should have these tiny, super durable cores, and we just haven't found them yet in these IDPs. So for now, the jury's still out.
But here's the thing. Whether they turn out to be primitive or truly primordial, studying these particles is already solving huge cosmic mysteries. Like one of the most basic ones of all, how do you build planets? How do you go from a giant cloud of gas to solid ground?
And what's amazing is that these IDPs hold the smoking gun. Because when you look inside them, you find these really weirdly shaped crystals. Some are like these long, thin whiskers. Others are like little flat plates. Now, you don't get shapes like that from cooling magma. No way. You get them when a solid crystal forms straight out of a hot gas. Think of how frost forms on a window pane. It's direct, physical proof of how the very first solids in our solar system came to be. It's incredible.
So in the end, that's what these are. They're not just dust. They're a library. Each tiny, invisible speck is a book filled with the history of our solar system. And maybe, just maybe, the story of what came before. We're only just now learning the language these books are written in. And that leaves us with a pretty amazing thought, doesn't it? What other stories are still locked away inside, just waiting for us to figure out how to read them?